Hello, can everyone hear me? Perfect. So, oh yeah. So I'm Poorva, and today I'm going to talk about how we can use bit representation of numbers for better inference on hybrid probabilistic programs. So let's start with the motivation. Real-life problems are complicated. They need hybrid models. They need a component of discreteness and continuity, both of them, to express the problem in its full glory. So some wide-known examples would include true-scale, spike and slab regression in computational biology, or modeling supply chain variables. And there are many more examples. So how do existing PPLs stand with respect to hybrid probabilistic models? I would like to evaluate them on two parameters, scalability and expressivity. On one hand, you have these universal PPLs which can perform inference for any probabilistic program that you can write, but they do not scale well on hybrid models. On the other hand, you have these special purpose PPLs which are very fast for the kind of program they support, but they impose non-trivial constraints on the kind of programs you can write in them. So what can we do to push the boundary of these special purpose PPLs? You can, for instance, take dice. It supports discrete inference, but it does not support continuous distributions, which does not allow it to support hybrid models. So one way to do that would be to use discretization. But you try to have a finer discretization for higher accuracy, and then you run into scalability issues. So can we do something else? We can do bitblasting. Let me explain bitblasting with the help of a simple example. Imagine that we have a continuous random variable x, which has a uniform distribution in the unit interval. Now you want to approximate it with a discrete distribution over fixed point numbers, and fixed point numbers have a fixed bit width. So let's take the example that it's 3 bits wide. Now a naive discretization strategy would be that you assign 1/8 probability mass to each of the values. But this might not scale well as you increase the number of bits. We can bit blast. What we can do is we can take 3 independent Bernoulli random variables, assign them with probability half, and combine them as a fixed point number. So now you have a uniform distribution over 8 values with just 3 random variables. Push it a bit further. If you have 32 bits in the representation of x, then you can have a uniform distribution over 2 raised to the power 32 values. That's more than 1 billion values with just 32 flips. Now, can we use this technique to have arbitrary distributions which are not uniform? And it seems we can. If we encode the dependencies of between these bits in a careful way, we can represent a triangle distribution, which then combines with a uniform to give you a linear distribution. And these linear distributions can be stitched together to give you a piecewise linear distribution. And as we know, we can use a piecewise linear distribution to approximate any arbitrary continuous distribution. Let's see it in action. So on the screen right now, you can see 2 different bit width approximation of a Gaussian distribution with bit width 4 and bit width 5 and different number of linear pieces. And if you just increase it a bit more with bit width 7 and 32 linear pieces, you get some approximation like this, which is visually indistinguishable from a Gaussian distribution. So we implemented this, ran some experiments on exhaustive, on a comprehensive suite of hybrid probabilistic programs, and it works. So yeah, thank you for listening, and